Hello friends, once again I am here in front of you to deliver my last lecture on the solid state, part 5. This is the last lecture for this chapter. Students, in previous class we have discussed various types of close packing in 3 dimension, HCP, CCP packing, and what are the percentage of voids, packing efficiency, and how many voids, tetrahedral voids, how many octahedral voids are there per unit cell, and the numerical based on the number of voids also I have given. One home task also given to you. I hope you have done that home task, and from your NCERT textbook also you have prepared a lot of problems. Okay? So today we will discuss about the crystal defect, that is imperfection. Students, we have discussed in crystalline structure the atoms spherically considered as spherical atoms packed to each other in a regular manner in 3 dimension HCP or CCP structure to form various unit cell, CCP, FCC, BCC or primitive structure. Then the atoms are located at the perfect lattice site, then that is the perfect crystal. But generally no crystal is perfect at normal conditions. Only at absolute zero temperature, whenever at minus 273 degrees centigrade, then only perfect crystal exists. But at normal condition, at these ordinary conditions, the atoms of spheres will be displaced from its original lattice site. That is, where the atoms are located at corner, let in BCC, atoms are located at the corners of the cube as well as at the body center of the cube. In FCC, atoms are located at the corners of the cube and face center of the cube. CCP, FCC. In HCP also there are different arrangements. But the atoms are displaced. There are various dislocations. Imperfections result due to the shifting of atoms from their original lattice site. As a result, various kinds of defects are found. So these are called crystal defects or imperfections in solid structure. Okay, students? So there are various categories: point defects, line defects and electronic defects. Write down very carefully. Point defect. Point means atoms. Atoms are considered as spherical atoms are considered as point. So point defect means that is the atoms will be displaced from its original lattice site and may leave the lattice structure or may enter into interstitial site. That is, the atoms or points will be displaced. So the defect arises is called point defect. Note down very carefully. And the line defect means a spherical atoms, already I have discussed, the spherical atoms are closely packed to each other to form various lines. So let a line of atoms will display from original site in the lattice structure. Consequently, the defect so obtained is the line defects. Okay. Another one is the electronic defect. In the lattice structure there are atoms and electron present. So due to the various displacement of electron may leave the lattice site or may enter interstitial site. Maybe electron excess, electron deficiency. Due to the electronic imperfection, the defect arises is the electronic defects. So this is not so important for our syllabus. So point defect is very useful for this topic. So let us discuss point defect. Point defects means atoms will be displaced. So point defects are of 3 types, broadly categorized. 3 types: stoichiometric defects, non-stoichiometric defects and the impurity defects. Write down very carefully. Stoichiometric defect means what? Atoms means points are displaced from its original lattice site, may leave the lattice structure or may enter to interstitial site. Due to the defect, the crystal stoichiometry does not change. There is no change in the crystal stoichiometry, means ratio of the atoms. Let 2 types of atom A and B. H to B, the definite ratio of H to B, the ratio of the atoms A and B will remain unchanged. But defect arises, but stoichiometry unchanged. That is called stoichiometric defects. Okay, stoichiometric defects are of 2 types. In ionic solids, there are 2 types of stoichiometric defect. Write down very carefully: Schottky defect and the Frankel defect. Write down, very important for board examination. Schottky defect and Frankel defect are the two important types of stoichiometric defect, where the defect arises due to the displacement of the atoms, but the stoichiometry remain unchanged, unaltered. So these two defects generally found in the ionic crystal, like sodium chloride, sodium bromide, silver bromide, etc. In ionic solids, due to the displacement of the ions from its original lattice site, may result vacancy defect, may result interstitial defect. What is vacancy? Vacancy means let an anion leaves its original lattice site. So the original site of the anion will be vacant. That is the vacancy defect. Let a cation leave its original lattice site and enter to the interstitial site. So the site of the cation will remain vacant. That is the vacancy defect due to cationic vacancy. Or may an anion leave the lattice site. So the site of the anion will remain vacant. That is the anionic vacancy. So due to vacancy defect or interstitial defect, in ionic solids, Schottky defect and Frankel defect is found. So both Schottky and Frankel defect are very important. Note down very carefully, students. Both Schottky and Frankel defect, the stoichiometry remain unchanged. So this is stoichiometry defects. How stoichiometry remain unchanged? I am discussing one by one. Schottky defect. In Schottky defect, in ionic solids, let these are the points in the lattice structure. Let this is these are the small ions, cations. Let an anion leave its original site. This is the anionic vacancy. Let a cation also leave its original site. This is the cationic vacancy, this is the anionic vacancy. So equal number of cation, one anion left the lattice. So equal number cation anion removed from the lattice. So the ratio of the cation A is to anion B remains same. Equal number, let two cation, two anion, equal number leaving the lattice. 3 cation, 3 anion. Equal number of cation anion may leave the lattice. As a result, the stoichiometry, the ratio of the atom remain unchanged. This type of crystal defect, stoichiometry defect, is called Schottky defect. Schottky defect is generally found in alkali metal halides. Group 1 metal, alkali metal halides generally shows Schottky defect because the size of cation, alkali metal ion, and the anion halide almost similar in size. That's why equal number of cation and anion may leave the lattice site. Consequently, stoichiometry defect, that is Schottky defect, is found. Very important question. Generally, what in board exam, in short question, it is coming the why alkali metal halide shows Schottky defect in 1 marks. Very important question. Next one is Frankel defect. This is also stoichiometry defect. Defect arises, but the stoichiometry remains same, unchanged. That is the Frankel defect. It is found when the cation is smaller in size, but anion is bigger in size. Those ionic solids, when the cation is small in size, let silver bromide, Br minus is big size, bigger in size. Silver cation is smaller in size. In this type of halides, generally Frankel defect. What is Frankel defect? Students, note down very carefully. Frankel defect means let cation small in size, cation leave the lattice site. Cation move from its original site and enters into interstitial site. You know, in interstitial there are voids, octahedral void, tetrahedral voids. So small cation leave its original lattice site and enter to interstitial site, because in interstitial there are voids. So there is a cationic vacancy at original site, but cation do not leave the lattice. Cation still exists in the unit cell. That is the ratio stoichiometric cation is to anion remain unchanged. Cation is not leaving the lattice. Cation is remaining in the unit cell. Just cationic vacancy and interstitial defect arises. So this is actually what? Vacancy defect plus interstitial defect. Why? Cationic vacancy and at interstitial cation is present. So vacancy and interstitial defect together form Frankel defect. and cation is to anion, the stoichiometry remain unchanged. So this is the Frankel defect. So student, there is a very important differentiation between these two. In Schottky defect, equal number cation anion missing the lattice site. That is, the density of the crystal will be decreased. In Schottky defect, very important for examination. In Schottky defect, the crystal density decreases. Why? Equal number of cation anion leaving the lattice, leaving the unit cell. As a result, density will be decreased, but the stoichiometry unchanged. This is the Schottky defect. Alkali metal halides. In Frankel defect, that is also stoichiometry defect, but cation is not leaving the unit cell. Cation still exists in the interstitial site. So the density remain unchanged. Very important short question. In Frankel defect, the crystal density remain unchanged because cation do not leave the unit cell. Cation remains in the interstitial site. So in Frankel defect, crystal density remain unchanged. Very important short question. Okay students, I hope you all understand whatever I have discussed just now. So this is over. Stoichiometry defect is over. The next one is non-stoichiometry defects. So this is just opposite to the stoichiometry defect. What is non-stoichiometry defect? Defect arises, point defect arises, as well as the crystal stoichiometry changes. Crystal stoichiometry means ratio cation and anion, that will be changed. Stoichiometry changes. So non-stoichiometry defect. Non-stoichiometry may arises due to metal deficiency or due to metal excess. Metal means generally metal from cation. In the ionic lattice, metal means cation deficiency defect. Let cation leave the lattice structure. So the cation is to anion stoichiometry changed. That is non-stoichiometry defect. Cation leave the lattice structure. So metal deficiency defect. Ferrous oxide may be doped with ferric oxide. Then ferrous ion Fe2 plus will be replaced by the ferric ion Fe3 plus. To balance the charge, there will be unequal number of distribution between the ferrous and ferric ion. As a result, the cation deficiency may be there in the structure. That is the metal deficiency. That is non-stoichiometry defect. I hope you understand. Okay. The last one is metal excess defect. There are two types of metal excess defect. Metal excess means metal will in excess amount in the unit cell. How? Metal excess due to anion vacancy. What? In your unit cell, what about the crystal stoichiometry between cation is to anion? Let anion leave the lattice structure, but cation remains same. So cation will be what? Excess, metal excess due to anion vacancy. Only anion leaving the lattice structure. There is a anionic site will be vacant, but cation remains same. So anion vacancy results metal excess. Very important thing, student, very important for your board examination. This type of anionic vacancy, the negatively charged anion leaving the lattice structure, anionic vacancy result, the anion vacancy may occupy negatively charged electron. So those anionic vacancy will be trapped by the negatively charged electron. This type of what? Electron trapped anionic vacancy. These are called F center. Very important. I have given a star mark here. Write down very carefully. This is called F center or color center in the crystal structure. Anionic vacancy, anion leaving the lattice structure. That anionic vacancy will be trapped by negatively charged electron. That point, particular site is called F center or color center. Why F center is called color center? Very important for board examination. These electron trapped anionic vacancy in metal excess defect, non-stoichiometry defect. This electron trapped anionic vacancy results definite color to the crystal. Like lithium chloride, LiCl crystal, you know, LiCl crystal, when metal excess defect arises due to the anionic vacancy, then automatically F center will be created. Negatively charged electron will be there. Then the shifting of negatively charged electron results pink color to the lithium chloride crystal, because the electron trapped in anionic vacancy F center may absorb radiation from visible light, jump to the higher level. only visible radiation, their frequencies, their wavelengths are visible to our naked eye. That's why it looks colorful. So due to the electronic transition in the F center, it generally absorbs radiations or definite frequency of the visible ray. Bibgyor, violet, indigo, blue, green, yellow, orange, red. Bibgyor. As a result, the crystal shows definite color. So lithium chloride shows pink color due to F center anionic vacancy trapped by negative electron, and its transition it causes pink color. Very important short question for board examination. Potassium chloride KCl crystal looks violet color due to F center anionic vacancy trapped by negative electron. So students, these are very important. Note down very carefully. Last one, metal excess due to extra cation. Metal excess, maybe it is a potassium chloride crystal. Any extra potassium ion cation may enter to the lattice structure, may enter to the interstitial site. Results, cation excess, metal excess. This is called metal excess due to extra cation in the lattice structure. So these are very important. I hope students you understand everything. The last one, point defect, last one is impurity defects. Impurity means the atoms, the point that is entering to the lattice, entering to the unit cell, that is impurity, that is not belongs to the original lattice structure. Let our lattice structure consist of A and B atoms. Let any C cation enter to the lattice structure, any unwanted foreign atom, that is the impurity. That results impurity defects. Okay, students. So I hope you all understand about various crystal defects, imperfection in lattice. So out of these, for board exam, you have to give priority on 3 defects. Very important. Again, I am writing here Schottky defect, Frankel defect, F center. Write down very carefully. These 3 defects are very important for your board examination. In details, you have to discuss from your reference book or NCERT textbook. So question may come from Schottky, Frankel and F center, and there are various informations related to Schottky, Frankel and F centers. Okay, already I have mentioned. So this part is over, students. This is over. Crystal defects or imperfection is over. So last part of this chapter I am going to discuss, that is properties of solids. So students, till now whatever we have discussed about various types of solids, crystalline, non-crystalline solids, various 14 types of brevis crystalline lattices. Out of them, very important one is what? Cubic crystal system. Cubic crystal system consists of 3 important unit cells: simple or primitive unit cell, body centered unit cell, face centered unit cell. In every type, what are the relation between edge length, radius, nearest neighbor distance, and packing efficiency, voids, different tetrahedral and octahedral voids, their relations, numerical problem, everything we have discussed. These are very useful. Whatever be the packing, there are some defects because the atoms or points are not located at the original site. Atom or point may be displaced from the original site, results crystal defects or imperfections. Various types of crystal defects already we have discussed. The last part is properties of solids. Properties of solids. Electrical properties, and magnetic properties. This is the last part of the chapter, magnetic properties. Okay, I will not discuss in details. Briefly I am discussing. You should follow your reference book, NCERT book, etc. Short question may come from this particular topic. So properties of solid, generally electrical and magnetic properties, important for solids. Electrical properties, certain solids conduct electricity, some solids do not conduct electricity. Okay, conductance, conductivity, there are 2 types of conductance. Current can pass through the metal, through the materials. These are conductors. there are two types of conductors, metallic conductor and electrolytic conductors. In metallic conductor, the carrier of current is electron. Free electrons carry the electricity from one point to another point throughout the circuit. In electrolytic conductant, free ions in molten state or in the aqueous solution state, the ions are freely moving here and there. The free ions carry the electricity throughout the solution. This is the electrolytic conductance. You know that. So, in our chapter, solids, crystalline solids, metallic solids, some are good conductors and some are non-conductors or insulators, and some are in between the conductor and insulator, that is semiconductors. This is a very useful in electronic gadgets. Okay, semiconductors means in between the conductor and insulators. So why their properties? Some are good conductors, some are non-conductor insulators, some are in between, that is semiconductors. This can be explained by band theory. You will learn about this in details in physics. Okay, what is band theory? In the solids, atoms are closely packed. In every atom, in the valence shell, the atomic orbitals are linearly combined with each other to form molecular orbital. In class 11, chemical bonding, molecular orbital theory, MOT. So atomic orbital combined with each other to form molecular orbitals. Then the similar energy molecular orbital form energy band. So in metal, whatever the atom present, their atomic orbital linearly combined to form molecular orbitals. The similar energy molecular orbital form energy band. So in the energy band, low energy band, generally electron filled up. Electron generally present to the low energy level, low energy orbital, band, etc. That is the electron occupied band. This is called valence band. Mind it, in band theory. Just briefly I am discussing. In detail I will not discuss. Okay, because time is very short. That's why I am just briefly explaining for your betterment. In band theory, electron generally present to the low energy band, molecular orbital band, that is the valence band. Okay, the high energy orbital form another high energy band, that is the conduction band, empty band. In conductor, the energy difference between valence band and conduction band is almost they are coincide. So electron can easily move from valence band to conduction band easily. Electron can move from valence band to conduction band. There is no energy gap between the valence band and conduction band. The electron can easily move. So due to the movement of free electron, it will conduct the electricity. According to band theory, that is why metals are good conductor of electricity, because in metal, the low energy band, valence band, high energy band, due to the molecular orbital, the energy difference is very narrow, almost coincide. That is why electron can freely move from valence band to conduction band. That's why metal is a good conductor of electricity. Okay. In insulators, non-conductors, like plastics, wood are non-conductors. Why? In non-conductor insulators, the valence band and the conduction band, the energy difference between the two is very large. The forbidden zone is very large gap. That is why generally electron present to the low energy band, valence band. The high energy band is empty. The energy gap, forbidden zone is very large. As a result, electron cannot jump from low energy band to high energy band. So electron remain to the valence band only. Electron cannot jump to the conduction band. That is why free movement of electron is not possible, restricted. So due to as a result, electrons are not moving freely in non-conductors. Consequently, those materials are non-conductors according to band theory. So last one is semiconductor. Very important. Semiconductor means the forbidden zone, valence band and conduction band. Valence band and conduction band, the forbidden zone is not so large. Let this is electron occupying band and this is valence band. In metal, it is the electron occupying band, valence band, it is the conduction band. energy increasing in this direction. This valence band means due to the what? Molecular orbital whose energy is similar. Okay, these are the valence band, electron occupying band. Conduction band, high energy molecular orbitals. Energy gap is not there. That is why electron can freely move. Free electron can freely moving. As a result, good conductor. These are metals. These are insulators. These are conductors. Metal means conductors. These are insulators. Look at this large gap. There is a large forbidden zone, large gap between the valence band and conduction band. So electron cannot jump from valence band to conduction band at normal condition. Not possible. That is why these are non-conductor insulators according to band theory. But in semiconductor, the energy gap is what? Small gap. This is the semiconductor. According to band theory, semiconductor. So at normal condition, at normal temperature, electron is not possible to jump from valence band to conduction band. That is why it behaves as insulator. But at elevated condition, led by increasing temperature or by adding a foreign material dopant, and foreign material may be doped with our metal, our crystals. Due to presence of foreign material, electron can jump from valence band to conduction band. Or at very high temperature, electron can jump from valence band to conduction band because the gap is small. So at normal condition, they are insulators. But at elevated condition, at high temperature or by adding dopant, impurity, it will be good conductor. These are called semiconductors. So semiconductor two types. Intrinsic semiconductor and extrinsic means what? At high temperature, it will become as good conductor. It will behave as good conductor. Intrinsic semiconductor. No dopant is added. But when impurity is added, due to presence of dopant, impurity, it will behave as good conductor. That is extrinsic semiconductor. Extrinsic semiconductor are two types. P type and N type. Very important, student, for board exam. In physics also you will be discussed. It will be this will be available in physics. P type and N type semiconductor, extrinsic semiconductor. A foreign material impurity is added to our solid. Due to presence of impurity dopant, it will behave as good conductor. Depending on the nature of the dopant, these are N type, N for negative, P type, P for positive. Generally group 14 solids, whenever doped with group 15 atoms, that will form N type semiconductor. And generally group 13 atom is doped with the group 14 atom, that will form P type semiconductor. It will be what? Discussed in detail in physics also. P type and N type extrinsic semiconductors. So briefly I have discussed. For your betterment, you should follow your reference book. Okay, student, this is electrical properties. The last part is magnetic properties. I am concluding little bit. I have to discuss more. Magnetic properties of solids. Students, magnetic properties of solid arises due to the electron. Electron is considered as a tiny magnet. Due to the movement of electron, there are two types of motion of electron. One is orbital motion around the nucleus of atom. Another is what? Rotation, movement of electron around your own axis. This is the spin only movement of electrons. Due to the two type of movement, there are some magnetic moment in the solid structure. Electronic movement. As a result, there are tiny magnetic and magnetic moment is there due to orbital motion or by electron spin. Okay. The magnetic moment, due to the magnetic moment, it will show magnetic properties. Now the alignment of the magnetic dipoles, whether it parallel alignment or non-parallel alignment, due to the various alignment of the magnetic dipoles of electron poles, there are different magnetic properties found. So, you know, some solids are highly attracted by magnetic field. Iron pin when brought to a magnet is strongly attracted. Paramagnetic. Ferromagnetism, ferrimagnetism, antiferromagnetism. Okay, students, diamagnetism. Some substances are when brought to a magnetic field, these are not attracted, these will be repelled by the magnetic field due to what? Anti-parallel alignment of the magnetic dipole in the structure. So these are not attracted by any powerful magnetic field. These are diamagnetic substances. So these are various 5 types of magnetic solids, different magnetic properties: paramagnetic substances, diamagnetic substances, ferromagnetic substances, ferrimagnetic substances, anti-ferromagnetic substances. Okay, student, these are the magnetic properties of solids. Revise it very carefully, thoroughly, read the NCERT textbook, followed by think about the concept inductive way, deductive way, analyze the content convergently, divergently, thereby do the problem from your NCERT textbook, from your previous board question paper, as well as from the MCQ problem from competitive examination. Success will be automatically, success will be there. So my well wish is always there. Do revision and do your best. Thank you.